All right, hello everyone. Welcome back to the hottest seminar. So this week we have Stefania Damato who will tell us about the groupoid CwF of containers.
Thank you. Thank you for the opportunity to have me speak at the seminar. So today I'm going to be talking about some still ongoing work that I'm doing with my supervisor, Torsten Altenkirch, at Nottingham. So, um, so to give a little bit of an overview of the structure of the talk, so in the first section, I'm going to be talking about categories with families, specifically in intensional type theory. So by that I mean in a setting where we don't have uniqueness of identity proofs, like we have in HOT, for example. And I'm going to highlight some coherence issues that come up in the setting. And so we're going to discuss two approaches of how we can try to fix this. So we're also going to specifically look at the example of a container model of type theory. And so we're going to try to fix this container model in two ways. So the first way, which is kind of the bulk of the talk, is going to be in section 2, where we define a groupoid CwF of containers. And then in the third section, I will present the second approach, which is we have to strictify the model. So make everything fit into a set. Okay, so that's the overview of the talk. So I'm going to start off with the first section, talking about CwFs in intensional type theory. So, okay, I'm going to start off with trying to explain a little bit what CwFs are. So a type theory is a formal system in which we can derive certain kinds of judgments, and a model constitutes a sound semantics for a type theory. And by a sound semantics, I mean that a model is an interpretation for a type theory such that if we have a judgment that can be derived in the type theory, then this judgment can also be derived in the model. So that's what I mean by model here. And categories with families, or CwFs, are one way to model dependent type theory or Martin-Löf type theory. And so one way we can think about CwFs is if we write down the intrinsic syntax of dependent type theory as a quotient inductive type, algebras of the signature correspond to CwFs. So when I say the intrinsic syntax of dependent type theory, I mean, as opposed to the extrinsic syntax of type theory, where we have pre-terms and pre-types and pre-contexts, and then we have some kind of typing relation to tell us what the well-typed things are. Here, I'm talking about writing the syntax intrinsically, or like as an inductive type. And so if I write that down as a quotient inductive type, and I take algebras in some sense of this signature, then that is what I mean by a CwF, or that is one way we can think of CwFs. So now I'm going to go into briefly over the definition, the original definition by Dibier. So a category of families consists of, so firstly, we're going to start off with a base category, C, of contexts. So we call them gamma, delta, and so on. And so the objects are contexts, and then the morphisms are substitutions between these contexts. So context substitutions. And then we're going to augment this category with first a presheaf tie. So this is going to be a presheaf on the category of contexts, and the object part is going to model the types in the type theory, and the morphism part is going to model the type substitutions. And then we have another presheaf we call Tim. And this is going to be a presheaf on the category of elements over tie. So that's that little integral sign. and that is referring to the category of elements whose objects are, well, something of the type that the functor tie takes in as input, and then tie applied to that input. So this presheaf term, the object part is going to model the terms of the type theory, and the morphism part is going to model the term substitutions. And then we have a context extension operation. So for any context gamma and any type in that context, we can extend the context gamma with the type such that we have some natural transformation. And yeah, so maybe this is a good point to say that I will be working in type theory. So that's kind of my meta theory. I know there are some category theory and type theory concepts, but kind of I'll be working in type theory for this talk. Okay, so the main problem with this when it comes to a UIP free setting is that the problem arises with the presheaf tie. And I'm going to try to illustrate this issue with some examples from well-known models of type theory. So the first example is the standard model or the set model. So if I have a type over a context gamma and the context in the set model are sets, then it's going to be a family of sets over the context gamma. And similarly, in the presheaf model, so if I fix a category C, then types over a context gamma, which in this case is going to be a presheaf, is again going to be some kind of dependent family of sets. And so when working in intensional type theory, i.e. we don't have uniqueness of identity proofs, in both cases, tie gamma forms a groupoid, not a set. So I guess historically, these examples made sense because people were mainly looking at extensional type theory, where we would have uniqueness of identity proofs. And so this wasn't really a concern. But if we try to work inside systems where we don't have UIP, then this is really something that we need to pay attention to. And so, yeah, so to reiterate, the problem is that in the definition of a CwF, types need to form a set, but in these examples, they form a groupoid. So we have a little bit of a mismatch there. So how do we solve this issue? So there's two ways that we can approach this. So the first way is we can force our existing models to fit the original CwF definition that I showed by Debier. And this would involve some kind of strictification. Another approach, which maybe one can argue is a little bit more principled, is to define some kind of higher CwF. So for example, some kind of infinity CwF, or we can kind of two truncate it, so groupoid CwF. And this would allow types to not just be sets, but they can be something higher, like groupoids or infinity types. But in this case, then we would have to prove some extra coherence laws so that we ensure that we still have the structure that we want out of our model. So in this talk, I'm going to show both approaches. I'm going to focus more on the right side of this diagram. So I'm going to focus more on groupoid CwFs. But I'm also going to show the approach of strictifying our model. And specifically, I'm going to consider one example of such a model, which is the container model proposed by Thorsten and Ambrosch. And we'll go over this in a bit. And before I proceed, I want to talk about some related work on higher CwFs. So Nikolai Krauss, in his paper, develops the notion of an infinity CwF. He does so in type theory, specifically in 2LTT. And he discusses the coherence problem, which asks, is the initial model or the syntax of an infinity CwF set truncated? And this isn't really answered, at least in 2LTT in this paper. And then there's this paper by Taichi Uemura, who, my understanding of this paper is that it proves that the initial infinity natural model is set truncated. The caveat to this is that the proof is not in type theory. So first of all, he uses natural model as the notion of model and not something like CWFs. And so, yeah, this is proved, but kind of not in type theory. Okay, and then we have a recent paper by Altenkirch et al., who define groupoid CWFs, aka two CWFs. So this is kind of like taking the infinity CWF and truncating it just at the two level. And in this paper, they show that the initial model is set truncated, the initial groupoid CWF. And then there's also, I think it's a preprint by Josh Chen, and he studies wild CWFs where context substitutions need not form a set. So when we think of the base category of the CWF, we don't ask that the HOMs have to be sets. They can be just types. And yeah, I'd like to point out that so groupoid CWFs are simple examples of what he calls two coherent wild CWFs. So what we're going to talk about and groupoid CWFs are a simple version of the wild stuff that is happening in Josh's paper here. So yeah, as I said, we're going to focus on groupoid CWFs, roughly following the preprint by Altenkirch et al. Okay, so now I'm going to kind of explain the main difference between CWFs and GCwFs. So GCwFs or groupoid CWFs. So in a groupoid CWF, the functor tie is now going to be a pseudo functor from a one category to the bicategory groupoid. So I'm using here the language that is presented in the paper by Arens et al. It's called Bicategories and Univalent Foundations. So essentially what this allows us to do is tie is no longer going into set here, but it's going into groupoid. And so this allows us to actually define types as they are defined, for example, in the set model, in the presheaf model, and as we're going to see in the container model, and it will actually fit this definition because those things are groupoids and not sets. So this is kind of the main difference between GCwFs and CWFs. The caveat is that we have additional coherence laws on types that need to be checked. So because now types are groupoids and not sets, equalities on them are no longer propositions, they contain data. So we have some coherence laws, extra coherence laws that we need to check. And these are specifically the coherence laws that we need to check for the groupoid case. And I'll explain them in more detail soon. But we have two triangulators and a pentagonator, essentially.
Can I ask a quick question to clarify?
Yeah.
These are not additional beyond the condition that it's a pseudo-functor. This is just spelling out what it means to be a pseudo-functor. Do I understand correctly?
Yes. Yeah, so I mean additional meaning additionally to the usual definition of a CWF, not additional to a pseudo-functor. Okay, so now I'm going to move on to the second section where I'm going to talk about the groupoid CWF of containers. So first of all, I'm briefly going to introduce containers. You might also know them as polynomial functors. So a set container is going to be a pair. So it's a set of shapes S and a family of positions P over the set of shapes. and we write it as S triangle P using this notation. And it's good to note that every container has a functor representation. So set containers have a functor representation as an endofunctor on set. And then we're going to also introduce a different type of container, which we call a generalized container. So a generalized container over a category C is going to be a pair again. So we have, again, a set of shapes, and this time the positions are going to go into objects of type of the category C. And we write this with a triangle with a little g here. And so once again, every generalized container has a functor representation. And this time, instead of going from set to set, it's going to go from the category C into set. And I'm not going to kind of go too much into detail about containers because kind of this talk is more focused on the CwF aspect. But containers are used in type theory to give us semantics for strictly positive types or well-behaved types. And the reason why we want a container model of type theory has to do with semantics of inductive types. And again, I'm kind of not going to go into that in this talk, but that is the motivation for wanting a container model of type theory. Okay, so now I'm going to review the container model that was outlined in the abstract by Thorsten and Ambrosch. It was a types abstract in 2021. So, so they presented it as a CwF. So they say that the category of context and substitutions is the category of set containers. So as we saw, we have a set of shapes and a family of sets over those shapes. And we also have container morphisms between them. And I will remind you that set containers have functorial representation on set. And then we have types. So types in a context gamma are going to be generalized containers over the category of elements of the functor representation of the context gamma. So now in the previous slide here, we have the category C. We're going to replace, or we're going to kind of initialize C as this category of elements. And so generalized containers, we said, will have a set of shapes and then a family of positions, which goes into the objects of this category. And these have functors of the representation as functors, and they're going to be of this type. Okay, and then we have terms. So terms of type A in context gamma are so-called dependent natural transformations from the functor representation of gamma to the functor representation of A. And I'm using this end notation here to denote this dependent natural transformation, so-called. And then we also have context extension, which is given by essentially components of the type A. And in order to give a little bit more intuition on the container model, I will be comparing it to the presheaf model. So you can think of the container model as maybe, okay, modulo the contravariantness of it, or contravariance of it. It's kind of like a restriction of the presheaf model in that we're restricting the functors to be container functors. So, so strictly speaking, the contexts in a container model are not endofunctors on set, they're containers, they're set containers, but they have a functor representation. So we can think of the container model as a restricted version of the presheaf model, essentially, because so as we're going to see, they're very similar. So contexts are functors. One is on COP and the other is on set. And Substitutions in the presheaf model are natural transformations between presheaves. In the container model, they're container morphisms, which in the container literature, they are fully, faithfully also natural transformations. So we have a fully faithful relationship between container morphisms and natural transformations between container functors. Types are functors, once again. So types in context gamma are very similar. And the terms, once again, are dependent natural transformations. Maybe the one thing to point out here is that this might look like it might raise some kind of size issue because we're quantifying over set here, but there is a way to make this smaller. So have an equivalent representation of this that is smaller using the Oneida lemma. So that's not really an issue. And then context extension, once again, is very similar. So kind of the way that the container model arose is that we restrict the presheaf model to just talk about functors that are container functors or that arise from containers. Okay, so we're going to talk about the coherence issues now. So the container model of Thorsten and Ambrusch suffers from the same coherence issues as the set and the presheaf models in that Ti gamma is a groupoid, not a set. And so recall that we had this diagram and we had two ways of approaching this issue. So in this section, I'm going to discuss the groupoid CwF of containers, and in the next section, we'll do the strictification. Okay, so now I'm going to go into a little bit more detail on the container model because this will be useful later when I talk about type substitution. So we said that the category of contexts is going to be the category of set containers. So if gamma is a context, then it's a set container. And then a substitution is going to be a container morphism. And a container morphism is made up of two maps. So we have a function on the shapes of the containers, and then also a function on the positions, but it's going the other way to the shape component. And then types, we said, so types in a context gamma, where gamma is a set container, are going to be generalized containers over the category of elements of the container functor of the context. And so one thing to note here, and I'm kind of writing down all of these types because, again, they'll be needed in the next slide, is that, so this PA here, we can break it apart into three components. So essentially what I'm saying is that any type in a context gamma has these components here. It has a set of shapes and then these three components for its position. And these come up just by kind of expanding what this category is. Okay, so now keeping all of that in mind, I pasted that here. This is kind of the hairy bit, which is type substitution. So given a container morphism, so if we have a substitution, a substitution gamma from delta to gamma, then we're going to roughly define the type or the generalized container A gamma as the following. So again, we need to define A gamma as a generalized container. So we need to give a shape and a position. And so the shape is going to be defined as this pullback here. So we're going to take the shape component of gamma, which I wrote the type of here. And then we're going to have this S map from the position of the type A. So this PAS here. And we're going to take the pullback of these two. And then for the positions, we're going to take the position component of the container morphism, so this one here, gamma p. And then we're also going to take this F component from the type A. So that we're going to put that there, and then we're going to take the push out of these two. And I use roughly here for two reasons. One reason being that, well, here I'm just giving you the X component. So I said that the positions have 3 components. So I'm just giving you this component here, but these two can be kind of read off from the diagrams. So this is kind of the most central thing. And then also I say roughly because if you look closely, you will realize that this arrow here does not type check. So PAF of SA is going to have this type, but that's so this thing here does not match this. So here we're really relying on the fact that the shape diagram commutes, because we know that PAS of SA is equal to gamma S of S delta. So that means that here I can use that. So there is some kind of transporting over part that is going on here. And that is why I say roughly. So you can already see that we're kind of going into this. We have like a dependent commutative diagram, if that's one way of describing it. Okay, but now I'm going to talk about how we represent these in type theory. So, so we have a trick for representing pullback in type theory. So we know this familiar trick of going from fibered to indexed representations. So if I have a map F from A to B, then I can also represent it as a type family. So this big F of B, I can just write it as a sigma of something in A such that F of A is equal to B. So this is kind of a well-known, the well-known indexed versus fibered representation, and I can go back and forth. And Ambrosch in the original formalization accompanying this types abstract uses this trick also to represent pullbacks. So if we have this pullback here, so if I have F and if I have G, then I can represent this as a type family H over C. And I just define H of C to be this F that I defined here, of GC, where G is this other morphism here. And so by definition of F, this is going to be this sigma type here. And this is kind of encapsulating everything that this pullback square is telling us, because I have something of type C and then something of type A, and then the commutativity property of this diagram. So this is a neat trick for representing pullbacks in type theory, and this allows us to represent pullbacks as families. The story for pushouts is that we don't have a trick for pushouts. So so the shapes are a pullback and the positions are pushouts, and so we represent the pushouts just literally as pushouts, and we take the set truncation of these things. So if you take the pushout of sets, you don't necessarily have a set as a result. But what we do is we kind of force it to be a set by set truncating it. And the pushout definition is the usual pushout definition, where we have an in left here, and we have an in right here, and then we have a commutativity requirement here. So this is specified as a higher inductive type. And then we have the set truncation here, where we have this constructor. So it takes any element of the pushout into the set truncation. And then this constructor, which says that, well, this type is going to be a set. And so kind of it would be useful if we also had a trick for pushouts, because so basically, okay, maybe I should mention that this is being formalized in cubical Agda. So there was already kind of a skeleton formalization of this with the types abstract. But what we did was we added the kind of, so before it was like sets being sets was implicit, and we made this explicit. And so we were actually being precise about this stuff in the formalization. And one thing that I've noticed while formalizing this is that proving things about the pullbacks is easier than proving things about the pushouts. And for the pushouts, because we don't have this trick, so this trick for pullbacks, so this trick for pullbacks allows us to, this trick for pullbacks ensures that we can prove, for example, equality of pullbacks directly, whereas for pushouts, we can only really prove equivalence of pushouts via isomorphisms, and then we have to use univalence. So it would be nice if we had a trick for representing pushouts in a way that we don't have to use univalence to show equality of pushouts. But that is the current approach that we're taking. Okay, so now I'm going to talk about the coherences that I mentioned earlier and how they show up for the specific case of the container model. So, okay, so first I'm going to talk about the triangulators. So these are the identity coherence laws. So, okay, so in CwFs, so just in standard set CwFs, we have to prove these equalities. So this first one says that if I have a type and I substitute it with the identity substitution, that is equal to the type itself. And then we also have that if I substitute A first with theta and then with delta, that is the same, or that is equal to if I substitute A with theta composed with delta. And yes, so this is kind of what I was saying before, is that so in order to prove this for the pushouts, we have to prove something like if I have a pushout and one of the morphisms is identity, then the square collapses. And for this equality, I basically have to prove that I can do pushout pasting. Whereas for pullbacks, it's a lot more direct. So these are kind of, these equalities already exist in the set definition, in the original definition of a CwF. And these are some extra coherence laws that now we need to prove. So what are these coherence laws saying? So let's look at the left. I will talk about the left coherence law. So let's take a look at what the left coherence law is saying. So these now are generalized containers, which we said form a groupoid and not a set. So the equalities between them are not propositions anymore. So now let's say I have this generalized container. So I have A substituted by ID, then substituted by gamma. Well, I can go to A gamma in two ways. I can either apply ID tie, so I can say, oh, A substituted by ID is just A, and directly go there under this gamma substitution. Or I can say, well, this is being substituted by two things here, so I'm just going to apply this rule to combine them. So now I have A substituted by a composition. And then I can just say, oh, but this by the identity law in the category, this should just be gamma. So there are two ways how I can go from here to here. And similarly over here, this is just swapping the gamma and the ID. And I have to show, in this case, because now these proofs are no longer propositions, that these two ways of doing this are equal. So that's what we mean by the coherence laws. Okay, so I'm going to try to sketch how we proved the left identity coherence laws to try to give you an idea in cubical Agda. Yeah, so this was a continuation of this formalization that already existed with the types abstract. So we're going to show this triangle. So we want to show that these equalities, so taking this path and taking this path, they're going to be equal. Okay, and so the proof sketch, I would like to thank Axel Ljungström, who actually gave a talk 2 weeks ago, because luckily for me, he recently moved to Nottingham, so now I can ask him all sorts of cubical Agda questions, and he's happy to answer. So yeah, this was done with his help. And I included a picture of him because he likes adding pictures of other people in his slides. So because we're working in cubical Agda, we're going to, first of all, write this triangle as a square. So it's nothing special. I just literally added an arrow here, and it's just refill. So now we have a square, and this square is a square of generalized containers. So all these things here are generalized containers. They're types in our model, and therefore generalized containers. Okay, so now we have this square, which we rewrite as this thing here. So a few things happened between this square and this square. So first of all, this is definitionally going to be gamma, and so this is, I believe, a consequence of how we define things in the container model. So in the container model, this definitionally becomes gamma. So actually, this is going to be refill, but also this arrow is going to be refill as well. So the top arrow and the right arrow are both going to be refill. But then these two are definitely not going to be refill. And we have to show that this square commutes. So the approach here is, so because this rule, and because this rule, so circ tie and ID tie, they were proved via univalence. So essentially how we prove them is we showed an equivalence between these two things and then applied univalence on it. The approach here is to kind of factor out univalence from the square. So you kind of want to write everything with univalence kind of, so you want all of the sides to be univalence of something, or univalence of some equivalence. So yeah, so here this is on these two sides is going to be the identity equivalence, because these two sides should end up being refill. And then here we have the equivalences that correspond to these proofs here, essentially. So what we've done is we factored out univalence from our square, and we also formulated a univalence principle specifically for these generalized containers. So UA GenCon says that, well, if A, where A and B are generalized containers, so if they're equivalent as generalized containers, then they are equal. And this equivalence we defined as a record type. And it involves basically comparing the components of the generalized containers. Okay, so first of all, we need to kind of factor out univalence from our square. And then we show that this square commutes by giving equalities for each of the generalized container components. So now we actually have to show that these things, like these arrows, are equivalent. And we do that component-wise by looking at all the separate components of the generalized containers. And finally, to get the original square that we had, so by that I mean this one. So to get from this one here to that one, we have to massage our equalities to match those we need via some lemmas. So for example, one lemma that we need is that this specified univalence for generalized containers, when we apply that to the identity equivalence, that's going to be equal to REFL. So that, for example, one thing that we needed to prove in a lemma and then kind of massage this square to get what we actually want. So that is how we proved this left identity coherence law in cubical Adam. And so that's kind of the approach, is to factor out univalence and then prove things in terms of equivalences between generalized containers, and then apply univalence at the very end, and then kind of massage the equalities that we have into those that we want. Okay, so kind of reporting on some progress that we've had so far. So we formalized the left and the right identity coherence laws, i.e. the triangulators. So using this approach that I just described, and the right identity law is fairly symmetrical to the left one. What still remains to do is this bigger coherence law, which is the associativity law, also known as the pentagonator. But now we're kind of confident that we'll be able to do this because we know the approach. So we'll follow a similar approach to what I described for the identity coherence laws, and it will be kind of more complicated squares, but we'll be following that approach. Okay, so that is everything I wanted to say about groupoid CwFs. And now I want to go into the second approach that we can take to solve the initial coherence issue that I described. Okay. So another way to solve the coherence issues in the model given in this abstract is to go on the other side of this diagram. So I mainly, the focus of this talk is mainly on this right side, and that's what we talked about in the previous section. But there's also a way that we can solve these issues by going the other way, and instead of thinking about changing the definition of a CwF, we stick with the original CwF definition and try to fit the container model into that original definition. And I'm going to show you a few tricks that we can apply in this case to obtain exactly this. Okay, so for the strictified container model, so now we're going to use the same ideas so the same container model that I showed before, but now we're going to apply some things to it. So first of all, I'm going to assume that we have this inductive recursive universe, U and L. And kind of the idea here is that U is going to contain codes for types, and L is going to decode those codes to the actual types that we want. And then we're going to say that the category of contexts and substitutions is the category of codes for set containers and codes for their morphisms. So essentially, we're going to have the same container model that was proposed in the abstract, but now we're going to work with codes for set containers and codes for their morphisms. But we can always kind of obtain the original set container by looking into what L maps the thing to. So I'm annotating everything that is a code with a hat here. So for example, gamma hat is going to be a code for gamma, and that that's going to live in U, because U is going to contain all the codes. And then in order to get the actual gamma, then I just need to apply L, which is like the decoding function on the hatted elements. So that is the trick that we apply here. And similarly for types, so if I have a context gamma hat, then the types are going to be codes for generalized containers. And here we apply a further trick, let's say. And we apply this so that we actually get strict equality. So in the laws that say, for example, that A substituted by identity is equal to A, there I want actual equality and not just isomorphism and not just equivalence, but actual equality. So in order to do that, we have to do this other thing, which is a form of splitting, where we represent types as codes for generalized containers, but what we do is we delay substitution. So in a bit more detail, a bit more concretely, so a type A hat in the context gamma hat is going to be, so we're going to fix a context. Let's say it's going to be delta hat. And then I'm going to have the code for a generalized container in that context, as well as a substitution going into delta. So the idea here is that A hat represents B hat substituted by delta, where I'm not actually doing the substitution. I'm just kind of keeping it there. I carry it around with me until I actually have to perform that substitution. And again, we do this in order for us to get strict equality in the equalities that we have to prove for a set CwF later on. Okay, so keeping this in mind that this is a type, then I can define type substitution. So if I have A hat like here, and I have a substitution gamma, which goes from theta hat to gamma hat, now I can define this as, okay, so I need to fix a context, and I'm going to fix theta hat, which is the domain of this gamma. And I'm going to keep the generalized container the same, or the code for the generalized container the same. And then here I'm just going to literally compose what I had before with what I have now. And so I'm going to compose delta with gamma, essentially. So gamma is the thing that I'm substituting over. So the way that A hat changed into A hat gamma when I substitute, well, the code for the generalized container doesn't change, but then I changed this substitution, and that's just type substitute. That's just function composition. And defining it this way will give us strict equalities. And so this fits into the original set CwF definition by DBA. So the collection of types is a set, since every component of a type A hat is of type U instead of set. So all of these things here that form a type live in U and not in set. Therefore, this is going to be okay in terms of H levels. And by that, I mean types will form an actual set instead of a groupoid.
Can I ask, what kind of things are type substitutions in this model exactly? Because the context are elements of U, right?
So yes.
Yeah, so what is the type of like lowercase delta or lowercase gamma?
Okay, so these ones you mean. So
Yeah.
these are gonna be so they're gonna be codes for container morphisms.
Okay,
So
so there's
they kind of
also there's another universe for those, or?
I think they can live in the same universe. Yeah, but they're gonna be so similarly, they're gonna be codes for set container morphisms, which we can then kind of extract the actual morphism by just looking into this L decoding function.
Okay.
Yeah. Yeah. Okay. Okay, so that brings me to the end of the talk. So to kind of recap what I've talked about. So we said that in a setting without uniqueness of identity proofs, like we have in HOT, categories with families raise coherence issues. And there's two ways to solve this. So either we redefine CwFs and look at some kind of higher CwFs, or we can strictify the models that don't fit in the original definition and make them fit into the set restraints. And we also focus in this talk on a specific example, which is the container model. So the first approach is proofs of the higher coherence laws is ongoing work, and we're formalizing this in cubical agda. And for the second approach, we use a few tricks that are well established. So we use an inductive recursive universe to lower the H level. And we also use this delaying substitution, which is a splitting technique. And yeah, that's it. Thank you. Thank you for listening.
Great. Thank you very much. Let's all visually applaud. And if you have any questions, you can. Okay, I guess we have a question from. No, maybe that was a mistaken click. All right. Yeah, guess if you have a question, just go ahead and unmute yourself. Niels, perhaps.
Okay, I guess I'm unmuted. So thank you for your talk. I have a bit of a question about the chosen approach. So one thing that I note in the talk is that one difficulty that you, or at least the way I interpret is like there seems to be like a difficulty to prove like the triangle and the pentagon coherences in the groupoid CwF case. And the thing that surprised me about this is why do you choose to use groupoid CwS? Because if you choose to use them, then indeed you force yourself to prove that. And this is something you should never want to do, because a nicer way to do this would be, for instance, to use something like vibrations or comprehension categories where you don't need to prove these coherences. They follow automatically. And that I think might lead to a simpler approach. So my question would be, what is the reason for using groupoid CwS rather than something like comprehension categories for this development?
Yeah, I think that's a good question. So kind of, I guess my answer would be that kind of CwFs are more type theoretical. So as I said, we can think of them as these algebras for the syntax of dependent type theory expressed as a quotient inductive type. So I guess kind of I'm used to working with CwFs because I do most of my work in type theory. I'm not really familiar. So obviously I know that there's other notions of model, and yeah, I know that, for example, comprehension categories are, I guess, more, they kind of capture more, or like, yeah, I don't know how to phrase it exactly, but yeah, I guess that would be my answer.
Thank you. And another question that I have for the strictified version, am I correct to interpret this as follows? So you have like a intensional type theory. Within this, you find some strict version of set, like the inductive recursive type, and then in essence, what you do is develop the container model in there rather than on that level. So you carve out basically a subpart where you have extensional type theory, and you work in that part to develop the container model. Is that a correct interpretation of what you're doing, or is there?
I think I think so, if I understood you correctly. So kind of that approach works because as I said, so every component of a type now lives in U and not in set. So therefore we kind of circumvent the problem that if these things live in set, then the collection of them will live in groupoids. But because they don't live in set and now they live in U, that problem is not there anymore. So yeah, I think it's how you described.
Okay, thank you.
More questions? Maybe I'll ask one while, okay, I'll ask one and then Steve. So maybe following on from the previous question. So how should I think about the relationship between the syntax of type theory and the notion of groupoid CwF? Like, are you thinking that I'm sort of weakening the syntax, or is this more like there should be some general strictification procedure that any groupoid CwF is a model, or what?
So when you say so you said groupoid CwFs and the syntax, do you mean the syntax of okay, so let me go back in my slides maybe. So
Right. So as you said in the beginning, I mean,
yeah,
the intrinsic syntax of type theory, as
yeah,
ordinarily defined, basically is exactly what a normal CwF is.
right. Yeah.
Right. So now you have this notion that's a little bit different, right? That's weaker. So should I think of this as being algebras for a weaker syntax, or is it rather that this is just some more permissive notion of model that could be strictified later, or what?
So I think it's the same. So so if we think of the intrinsic syntax, that's a quotient inductive type, and now we have groupoid CwFs, and yeah. So in this paper, so this is a new edition. So I think there they also use some inductive recursive representation of like in order to have groupoid CwFs. So I'm not sure. Yeah, I think maybe this this paper might have more of an answer for your question.
Okay, thanks. Yeah, I mean, I see like the motivation makes sense that this thing that you want to be a model isn't a model, so you have a notion of model where it is a model, right? But then, of course, the question is,
Yeah.
what's the relationship between the new notion of model and then the thing we're trying to model in the first place? All right. So
Right. Yes. So my understanding is that in this paper they show that the initial 2CwF or groupoid CwF is set truncated.
right.
And that I guess is the syntax or the initial model.
Right.
But yeah.
Okay. Yeah. Okay. Great. I think that might be the answer. Thanks. So, Steve, go ahead.
Just to give a reference for a two-dimensional CwF, you might look at Mike Schulman's paper on univalent universes in infinity toposes, where he introduces a notion of a, what is it called? Locally representable notion of fibered structure that's based on what is essentially a two-dimensional natural model, which is, of course, the same thing as a two-dimensional CwF. And then he develops that theory and he makes good use of it to prove the existence of univalent universes in various presentations of infinity toposes. So that might be useful.
Okay, thanks. Can you repeat the name of the paper if you have it?
Sure. It's by the author is Michael Schulman, and the title is All Infinity One Toposes Have Strict Univalent Universes.
Okay.
And I'm looking at sections 2 and 3.
Okay. Okay. Thank you.
You're welcome. It's
Anyone?
not for the faint of heart, but it's worth working through. Yeah.
Okay. Thanks.
Yep.
Okay. Anyone else? Maybe I'll ask another question. So how many more coherences are there? So I guess there's for terms, there's also going to be, like dependent triangle and pentagon laws.
So there so for terms there shouldn't be, and the reason is that okay, which slide am I looking for?
Probably later.
So here so even in the set model and in the presheaf model, the term part doesn't really present a problem because those things form a set and not a groupoid. So actually we don't need higher coherences for terms. The real problem is types. Yeah.
Okay,
So
then,
really,
yeah.
So really the extra coherences are going to be those three coherences, so the triangulators and the pentagonator. I guess also kind of so we would have proofs that, for example, types form a groupoid and terms form a set. And I guess also that contexts form a set. Yeah.
Okay.
But yeah, there aren't too many in the two CwF setting. But the higher you go, obviously, the more you're gonna have.
Sure. Okay, well, that's good news. Anyone else? Okay, well, let's thank the speaker one more time. And
Thank you.
I will just remind you, so our next talk is not in 2 weeks, but in 4 weeks. So on December 4th, we'll have Matteo Spadetto speaking about TBA. So thanks, I'll see you then.